welcome. And just there has been some updates since I released this transistor amplifier calculator, and let's just go over it again. Yeah, it should be a help for seeing what happens, simulate, calculate some basic amplifier types based on transistors. And you can select over here until now 3. Later on, as I have the time, I'll add more. And if you select one, some of the fields will change over here and down here, depending on what you select here. So you have some supply voltage. You can see the schematic here, make it big. And this is now zoomed, so it's out of the the frame right now. Normally it's smaller. And if it's not, I'll fix it later. You can put in the voltage, the typical current running through over here on R3, R4 for this emitter, for instance. Choose a transistor model, just pre-selected the most common for hobbyists, etc. The typical gain is 100, just leave it there. And the bypass capacitor is the one down here, R7. What I call as REC, and you can change the value here if you want. Load resistance, that's the output resistance on the load, whatever load you have. And if you, for instance, change to place AB power amplifier, you will have a speaker resistance instead. And everything is reflected in the calculations right away. So yeah, and this is the basic side on the left side here. Inclusive, you can download the data for clipboard, XML, for whatever, CSV, comma separated file, and a list of resistors, capacitors that you have at the moment here. On the top, should start with that. This video here will be substituted with this new version. Discord, there's a place where you can comment whatever, and come with suggestions and feedback. That would be nice. Not only good stuff, but suggestions for improvements, etc. If things fail or whatever here on this calculator. Features is just a list of features. And you can, if you're on mobile or tablet, you can use this for zooming in or out. You can even switch to dark mode and back again, and that can be quite nice in the evenings. Yeah, and what do we have here? You can give it a name for when you download down here. And there will be a timestamp for it too. Yeah, depending on what project you're running. So this is just for, yeah, exactly. And here's some results in the middle. And the idea is that you can actually just change, let's say here 15 volts or 20 volts or something, 15. It will change immediately, 15 volts, calculate other values. Yeah, and with a bypass capacitor, if you change that to no, you'll immediately see voltage gain falls to something less. Max gain again, let's keep it there for the common emitter. Calculation of least minimum capacitance can be higher than this, no problem, just not less with the frequencies or with the things selected here. And there are some graphs where you can see more or less. Down here it says cutoff frequency on the high side 14 megahertz with this transistor, etc. And you can see the points on the curve here for the gain, voltage to voltage. Yeah, left side, middle side, we see here typical transistor output characteristics. Now I changed up here to 15 volt. So I should probably change the drop to 7.5. Let's just do that to see what happens. 7.5. just to be in the middle, and you can see it's way better, it lies better. There is a symmetric string of around 7 volt. If we go back, oh, didn't do that right. If we go back on the 6 volt, you will be able to see how it can't swing so much as before. So it's playing around with this collector current standard. Could be 1 or 2 milliamperes, but yeah, that's just. What do we have formulas used? Will be extended a little bit, but that's just for, yeah, see how we have a list of it. Notes, assumptions for fixing a little bit what parameters the transistor has, and some fixed assumptions about how a transistor reacts on voltage collector base minimum, and the minimum for the voltage drop over RC. In some cases that's needed. Yeah. On the right side we have the advanced stuff, and that could be, first of all, you can find an explanation here on what you can choose in this one, and depending on what amplifier type you select, it will change over here. There are some that are better for, that's the way it's constrained mode, is how you calculate the stuff. So some fields are dependent on others, and if you calculate it different, you can go the other way around with calculations, and that's somehow affected with this one. But just leave it with if you select over here, it will jump to a typical used, or the most used actually, for the amplifier type. And then there's, in some cases, a second option if you want something special. So let's go back to the common emitter. And as you saw, the schematic changes as you change the amplifier type. Yeah. And the green fields, marked green, they are for this characteristic, or this way of calculating it with based on the gain and the drop of over the voltage drop over RC, or R3 here. And you can change the gain if you, it's a target gain. So you can change that, and it will calculate the final obtained gain. And of course, it has an influence. The bypass capacitor with resistor has an influence on that. If you don't use that, let's just see it. This is the normal resistor down here, R4. And if you use this bypass capacitor, you can choose no. And you can see the gain is way less without this one. Yeah, and the voltage drop, we have 15 volt. Maybe we want a voltage drop of 7 over here, and we'll recalculate, and you can, yeah, see a little bit there. Target low cutoff frequency. That is the lowest cutoff frequency on cutoff frequency on the low side. And for sound, you maybe go down to 10 or 5 or 4 or something like that. You can try out here, and it will only influence the capacitors. Let's just try 4. Let's see what happens. You have new curves, and you can see they have changed a little bit on the values. And they are here. It's minimum values. If you go higher up, it's no problem. At least for those two. Yeah, for all 3 of them actually. And some transistors maybe have a base emitter drop of 0.6 or 0.65 volt. You can change that. You can normally just leave it. It's estimations. Everything is estimation. It's a simulation. Real world can be different. And yeah, and for instance, we have here, if we have a collector current of 2 milliampere, we can change. There's a certain voltage going or current going through the base of the transistor based on what you have of current here. And if you, the normal ratio between what's going through R2 to the base, that's reflected here. Normal rate is 10, But you could say, let's go higher, and let's see what happens with this R1 and R2. And let's just go on 100 and see what happens. There. And you can see they get way less. And at the same time, you can see some impedance change down here for the input impedance and the output impedance. And let's just go back. And you see they are way higher now for the in and output impedance, or input impedance at least. So this changes, of course, R1 and R2. Let's go again, 100. Yeah. So that's just playing a little bit around with voltage ratio between what's going down in R2 through R2 compared with in current through R2 compared to current going into the base of the transistor. Yeah, source resistance over here, just leave it if you don't know what it is. Basically, it's a question of what we have here in R5 source, and the voltage coming out here compared in relation with the current going through here gives a resistance estimate, etc., etc. If you have some other preamplifier on the left side, this could be calculated further exactly, etc. But this is, depending on what you do, you can just leave it or try out something else. Very interesting down here, we have the resistor series, and there are suggestions for the standard values. And you see now 62K over here on R1. And if we change that to E96, it will be way more graduated in various ways. So that depends on what resistor series you go with. Normally it's E24. And you have the color coding also in text, because sometimes colors are, screwed by the screen or whatever. If you push down here, you would get it even bigger for 5 seconds. So it makes it a little bit easier to check the colors. You don't have to look it up. And what I love most is one of these things coming with suggestions, because you have a value and then you have to find what's closest, and this actually does it for you. Yeah, plot gains, plot downloads, again, based on the name you give up here, you can change it as you want. You can download gain plots. That's the same as you see down here. You can even mark some spots. And then let's just take the swing plot this time. And I don't know if you can see it. No, you can't see it. But then you would be able to see even the marks on the mark you left on the swing plot when you download it. And you can of course get the same for transistor output, or simply you can print the whole page. Maybe you can't see that. Oh yeah, you can see it. Yes, you can print the whole page. The inputs are up here on the first. Then you have just short what schematic, the results, etc., the curves, graphs, gains, etc. This one, transistor characteristics, the formulas, and some notes. Everything as a PDF, quite nice. So you can store it for later, turn back, put in the dates or whatever, take it somewhere else, chat with your friends. And also here, these CSVs, downloading the CSV, you will probably, let's take the XML, you can see that. They are nice for communicating with friends or share it with friends, that you have all the data fixed to something. And here you can say, see the suggested name, or the name you can change in the input field. You can see the date, time, and you can see the values that you have in the inputs, and also the calculation, the results. You can share it with your friends, discuss it somewhere else. And this is an XML, so this is quite a little bit of computer format. But the CSV should have the same information. Maybe it needs some updates, I'll do that. And clipboard, you can actually copy paste with just pushing here, and you have it in the copy paste. And you can paste it in somewhere else for a chat. So it's quite nice to discuss settings and stuff and get a fixed something of. I had this idea. I ended up with, maybe I don't want 12 volt, I want 15 or 20. What happens when I do that? What resistors do I need? So this is just simulations, estimates for getting started. And transistor gain is often just an estimate too. Maybe you can set it higher. Maybe you have a transistor less, with less gain, etc. Yeah, let's see. If we now change to common collector, schematic changes, and you have fewer possibilities. Target low cutoff frequency is here set to 4 Hertz. Yeah. Oh, and you have possibilities to calculate too. And of course, RC does not exist for a common collector, and that's why it's left out here. And you can see the output impedance is quite low for a common collector, for instance, as there's no resistor up here, and if you take the class AB power amplifier, then again you have these two, typically tip 31, tip 32, and again you have a low impedance, so you can really let some power out here in the effect. And this just here in the middle, that is a VBE multiplier, which there's a short description how to set it. And yeah, that's a quite nice thing. There are other schematics where you have 2 diodes instead of this VBE multiplier, and 2 diodes doesn't work. I've tested it. It's not good. Being able to adjust with this potentiometer here on the VBE multiplier, adjust the voltage difference between these 2 base pins is crucial for getting it to work. 2 diodes, that's a random thing if it works or not, just on this class AB power amplifier. Yeah, and you see for the class AB power amplifier, there is a section more here. The quiescent current going through on the right side is this one. Just, assumption of 2 milliamperes, can be 5, can be 20 milliamperes. If you have power transistors there, like tip 31, 32, that's no problem with 20 milliamperes, something like that. It's just, you just need as much milliampere as any crossover distortion disappears, actually. And the beta value, the amplification value of the Q3 and 4, these two, Q3 and Q4, that's just an estimate, 50 year, could be 40. It's just a fixed number for now. And the VB multiplier drop, I had one on 1.23 volt, so adjusted to that. Start out with 0.7 volt and then slowly turn it up and until you see that the distortion disappear. If you have a possibility to measure the current consumption, then watch it that it doesn't, rise more than 2 to 20 milliampere while you adjust it. Yeah. Our load is, of course, for the class A power amplifier, a speaker. On the left side over here, that would be a speaker through a capacitor of maybe 1000 microfarad. And you have some other data here, max output swing, etc., etc., max output power. It's an estimate, and depending on what you have a signal and how loud you make it, you will maybe get that as a maximum. Impedance is just actually calculated as half of the speaker load here, the speaker resistance. Yeah. Any suggestions? There is a rough estimate of how good the transistor output characters are. If we... No, we can't. Okay, that's okay. It's based on calculations based on this symmetry mode. If you go on the class AP over to modern mode, you could actually change the drop over RC, that's the same as R3, to maybe, let's say 4. And you can see down here how this straight away changes, that you have less symmetric swing. On one side, you can maybe, to the left, you can swing 10.39 volts, but on the right side, you can actually only swing 3.4 more or less volt, and that limits how far away you can swing from the cue point. And there's a warning down here. It's only for consumer grade electronics, just a rough estimate. But let's just go back here on the original, and you'll see that's way better. Oh yeah. So this is now with induced features, updates, etc. And over time, I will make more on this. There can be some quirks here and there. And with time, I'll add some more, maybe the common base amplifier, other stuff. And so, yeah, that's that. Hope you will have fun and enjoy it. Like, comment, suggest, whatever. And thanks for watching.